In Section 4, Chapter 8, the central limit theorem is discussed. If all samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution. This approximation improves with larger samples. If the population follows a normal probability distribution, then for any sample size, the sampling distribution of the sample mean will also be normal. This is what this means. If the population distribution, in other words, there's a variable x, for example, the age of students at a university, of all the students, so that will be the population. This mean here will be the average age of the students, which is right at the center of the distribution. And you're going to have here on this side the very young people, maybe somebody who is 16. And at the very extreme here, you may find maybe somebody who is 62, let's say. So you have a wide range of ages. And right in the middle, some age around 2021, you have the mean or average in the population, and notice here x. So if the population of the variable in the population is normally distributed, then when you take a sample of any size, random sample from the population, and you calculate the mean of that sample, well, that mean is going to be just 1 in this normal distribution of means. So if you repeat that process again and again and again and again, in theory, that process is repeated indefinitely or infinitely, then all x bar possibles will be obtained from repeating the sample. Suppose that sample is of size 8. So you take 8 people, 8 students, and estimate their average age. Notice that this is x here, and this is the average. So all my results of my samples, averages, will be closer to each other than the original x variable distribution, because the original x variable is all the ages. And this one is the distribution of all possible sample means. So they will be around the mean of the means. And the central limit theorem says this mean of the means is mu, which happens to be this value. The mean of the sample means is the population mean. And the distribution of this data, the samples, will follow a normal distribution regardless of sample size. It doesn't matter what the number here is. Now, if the distribution of x in the population is unknown, or we know that it's not normally distributed, then the sampling distribution of x bar can also be, again, normal, and the mean here will be also in the middle, as long as n, the sample size, is at least equal to 30. So in the case of students, if you select at least 30 students in every sample, and you repeat that thousands and thousands of times, then you're going to get this kind of distribution of your data with low values of the mean, repeated with fewer times, This is the height here is a frequency, and values in the middle around the population mean will be repeated the most, occur more often, and values around here will be repeated less. Now let's go back here and read again. If the population follows a normal distribution, then for any sample size, the sample distribution of the sample mean will also be normal, which is the top graph that I just showed you. If the population distribution is symmetrical but not normal, the normal shape of the distribution of the sample mean emerges with samples as small as 10. If a distribution is skewed or has thick tails, it may require samples of 30 or more to observe the normality feature. The mean of the sampling distribution is equal to mu, and the standard deviation is sigma over the square root of n. If we square the standard deviation, we will obtain expression here. So the central limit theorem can be displayed here or illustrated. The population of values of x, notice this is x, x, x every time, may be this shape, or that shape, this shape. Okay? You're probably familiar with this. This looks like a uniform distribution. Well, if you take repeated samples of size 2, then the distribution of those samples will follow this shape. If you take repeated samples of size 6, then the distribution will be like that. Notice how it becomes already normally distributed. And finally, if you have at least 30, in this case 30, and repeat the samples many times, or the sampling process is repeated many times, well, you get the normal distribution every time. This is an example. Spence Sprockets Incorporated employs 40 people and faces major decisions regarding healthcare for these employees. Before making a final decision on what healthcare plan to purchase, Ed decides to form a committee of 5 representative employees. The committee will be asked to study the healthcare issue carefully and make a recommendation as to what plan best fits the employees' needs. Ed feels the views of newer employees toward healthcare may differ from those of more experienced employees. If Ed randomly selects this committee, what can he expect in terms of the mean years with Spence sprockets for those on the committee? How does the shape of the distribution of years of experience of all employees, the population, compared with the shape of the sampling distribution of the mean? The lengths of service rounded to the nearest year of the 40 employees currently on the Spence Sprockets Incorporated payroll are as follows. So these are 40 numbers of number of years the 40 employees have with the company. And I have an Excel file that has the same numbers. That Excel file is right here. Okay. First employee 11 years, second 4, third 18, etc. It's the same numbers that you saw there. Now, what is a possible example of size 5? I get the first person and the second and the third and the fourth. I'm just repeating the numbers on the left. And the fifth. That's a sample of size 5. But I can also do 11 and 4 and 18 and 2. And then my fifth person, instead of being my fifth person, I'm going to select the sixth person. And then again, another one, 11, 4, 18, 2. And now I select the seventh person, and that is a 0. As you can see here, the fifth person is 1, the sixth 2, the seventh 0. Then if I continue doing this, just selecting in the fifth position the following, I will get a lot of samples. So please notice this is sample 1, sample 2, sample 3. So I'm doing a sampling process or obtaining a sampling distribution. To obtain an accurate sampling distribution, I will need to repeat this sampling many times across here. But My sample size in this case is 5. Each sample has a size of 5. Okay, and I can get an average here. See, that's the purpose of doing the sampling in this case. D4 through D8. See, I obtain a sample of an average of 7.2. If I copy to the other two, then I get 7.4, then 7. As you can anticipate, and this is very important, these numbers that I will obtain as averages, they will never be equal to 0 or 1. They can never be 18 or 19 as shown here, because those are extreme values. My averages are always going to be somehow or somewhere in the middle of all these values, or close to the middle of all these values. So the sampling, the central limit theorem says if you repeat this sampling hundreds, thousands, and thousands of times, and you calculate the average every time, then you're going to get a distribution that the larger the sample size, the more it becomes a normal distribution. And then if you're curious about the number of samples that we may be able to obtain, I had a previous notes here. The formula is the combination formula that you saw before. It'll be 40 people, and you select a committee of 5. So the calculation is 40 factorial divided by 5 factorial, and then 40 minus 5, 35 times 35 factorial. And actually, you can simplify that by multiplying 40 by 39, by 38, by 37, by 36, and then you don't continue with 35 and 34, etc., because it will cancel out with the 35 factorial in the denominator. And that divided by 5 times 4 times 3 times 2. Okay? Then you obtain an answer here. You can do this with TI-80s, or I think there is you enter a number, then you select in math the combination, and then you enter your little n, and then enter, and you get the combination. But in Excel, you can just type equal com, bin, open parentheses, enter your capital N, and then your little n, the total number, and then how many at a time do you want. And the total number of samples is 658,008. So if you can do this, repeat it, 658,008, then you're going to get 658,008 averages. And then what is the distribution of these averages? Using a range at a time. It's not like you're going to use a frequency 7.2, how many times occurs. No, you're going to get a largest value, minimum value, and then you divide that by 5 categories, let's say. And once you have that, then you're going to get the width of each category. So if you get like a 0.3, what does that mean? Well, you start, supposing lowest value was 6, between 6 and 6.3, between 6.3 and 6.6, between 6.6 and 6.9, etc. So you have an interval. And then you calculate the frequency that occurs within each interval. And so if you do that, you obtain, in this example, the population is distributed like this, and this one here on top is actually just frequencies. 0 occurs 3 times, 1 occurs 6 times, and you can go back to the data and confirm that. Okay, we have 0, notice 0 1 time, 2 times, right? I think I skipped 1, and 3 times. So that is 0. And then you do the same for the other numbers, and then you get this kind of frequency, which is not normal. I'm sorry, distribution, peak, and then a long tail here. Now, these numbers here are more, these are the frequencies for 25 samples only, and 5 employees every time. This is again 25 samples, but with 20 employees, and the distribution begins to look more normal. All right, so that is the end of this presentation, and we'll continue with the following section.